Hello, and welcome to another video of Renaissance Timing University. I'm Steven Gutierrez, and in this video, we're going to be talking about random jitter and deterministic jitter. So let's take a look at a signal in the time domain. This is voltage versus time. If we were to observe this signal and just watch it cross an infinite persist and map every single time that it crosses this reference point, we could map the random jitter. So let me just kind of zoom into this region. And again, we've got a reference here, and we've got the crossing point here. And as we observe this more and more crossings and more waveforms, we're going to develop, and we can statistically look at those crossings, and we would end up with this Gaussian distribution. And as we have more and more crossings, statistically, they can show up earlier and show up later. And so this Gaussian tail starts to grow more and more. So that's what the random jitter looks like. In the frequency domain, it's simply the phase noise plot. So this noise floor here, this profile, is your random jitter. Now, deterministic jitter in the time domain is going to show up as another crossing. So let's say this waveform all of a sudden jumps and it crosses earlier. So let me get rid of this little rectangle. And now this crosses earlier and sometimes later. And likewise, this crosses earlier and sometimes later. So we zoom in, we have these kind of two regions where the signal is crossing. This also has a random distribution across the center of that crossing. And if we find the center of this crossing, this distance is your deterministic jitter. And this is fixed. Now there is a spec called total jitter, which takes into account the growth of these two edges. So as we capture more waveforms, this edge grows out, and that's what we call total jitter, because it takes into account not only the deterministic jitter, but also the growth of the random jitter. So that's how it shows up in the time domain. In the frequency domain, it's simply a spur. And depending on the phase noise analyzer you have, it can also give you and quantify how much noise or RMS noise, or it kind of quantifies the phase noise that's contributed by this spur. Now, the random jitter is inherent to the design. It's part of the technology. It can be due to your input reference as well. And there's not really much you can do to improve or change the random jitter. That's probably one of the main specs of the device. But when it comes to deterministic jitter, you can try to root cause to see where it's coming from. So it could be coming from a noisy power supply. There could be another signal on the board that's coupling onto the signal that's under test. And to really figure out where it's coming from, you can get a reference measurement from us, and that way you can understand if that signal shows up under ideal conditions. So if you ask for a phase noise plot, is there a spur on the phase noise plot? If there's not, then we can start looking at the board to see maybe where that spur or that noise is coming from. So this is a quick intro, but we do have a lot more information on another video that talks about the sources of jitter. So you can check that out on Renaissance Timing University. And thank you so much for taking time to watch this video, and check out more of our videos on Renaissance Timing University.